Hello. In this video, I'm going to go over the aspects of experiment zero kinetics, particularly how the trials work for the reaction we're going to monitor. So first of all, what are we trying to do in experiment zero? We want to determine the kinetics of the following reaction. So it's the persulfate ion and iodide reacting to form sulfate and iodine. And our goals for this part of the experiment is to find the rate law, find the rate constant K in appropriate units. So let's remind ourselves what goes into finding a rate law. What are the pieces of it? Well, first of all, in the equation, the expression, we have the rate, R, and it's equal to a couple things multiplied together. What are those things? The first thing is its rate constant, K. And then what are the other parts of a rate law? The rate law shows us how the reactant concentrations affect the rate. So we have the concentration of persulfate to, notice there's an N, that's the order for persulfate, and iodide to its order. So the goal of our experiment is to find those pieces. We need to find K, we need to find the order of persulfate, and we need to find the order of M. So how exactly are we going to do that? So you see before you reaction number one, the one that we desire to monitor. Now, the issue is if you pour the reactants together in a beaker, you're not really going to see a lot happening. And we need to have some way to obviously tell that the reaction is going. And so, fortunately, there is something else we can add to the reaction to have a visual indication that it is making product. And that thing that we're going to add is starch. It's the same household starch you can buy at the market, but when starch and iodine, I2, combine together, they form a complex, an association that is actually a very vivid blue color. So if we put starch in with the reactants in, say, a beaker or a flask, then we can see that product is being made because as you're building up iodine, it will stick to starch molecules and you'll get a blue color. Now, the problem is that if we just mixed those things together, the reactants and starch, then the moment we pour them all in the same beaker, it would immediately turn blue. So while that's helpful to know we've made product, it's not going to give us time to take down a measurement with a stopwatch because it's going to immediately change. So we need a delay so that we can tell when the iodine starts building up in a significant concentration. And the way we do that is by adding something that will compete with the starch for the iodine. And that is going to be thiosulfate, S2O3 2 minus. And what it does is it reacts with iodine to form S4O6 2 minus and I minus, both of which are colorless. And in fact, it does this at a much faster rate than the starch association reaction. So in this diagram, if we have S2O8 persulfate, the red reactant, and iodide reacting, they'll make sulfate and iodine. But before the iodine can combine with the starch to turn blue, the thiosulfate is going to use it up and turn it into a colorless iodide product. So with all of these things together in the same beaker, we actually won't see a color change. So we can imagine if I mix all of these things together, the reaction number one will be happening, but we won't see any color change because of the thiosulfate. Now, the thiosulfate will prevent the iodine from turning blue so long as it's still present to react. But what happens when the last ion of S2O3 gets used up? Well, now there's nothing to prevent the iodine that's being made by reaction one to turn blue. So after this time delay, there will be a sudden blue color change. And this can be more accurately monitored with a stopwatch. How long does it take for all of the thiosulfate to be consumed and the blue color sort of coming forward? So we'll take down those measurements. How long does it take for all of my thiosulfate to get used up? How long does it take, therefore, for my solution to turn blue? From this, we can use stoichiometry to figure out how the concentrations of reactants in reaction one are changing. Because after all, from first semester, we see that two S2O3s has to combine with one iodine. So there is a clear stoichiometry relationship between if I know how much thiosulfate got used up, I can turn it into how much iodine was being made. And from reaction one, again, with coefficients, I can turn that into how much per sulfate had to be used up in that time period as well. And so from that, we're going to get our first data point for this experiment. So the trials will look a little bit something like this. You'll have two flasks and a small beaker. In the small beaker, you'll have sodium thiosulfate, Na2S2O3, and starch. In flask one, or rather flask A, you'll have the first reactant of reaction one, the persulfate, in the form of ammonium persulfate. And in flask B, you'll have the other reactant of reaction one, potassium iodide. You'll mix them together in the beaker with the sodium thiosulfate and the starch, and you'll observe that there will be no color change upon initial mixture, but that's when you'll start the clock. And over a period of time, you'll see a sudden blue color emerge. And that's when you'll press stop and you'll take down your first time point in the kinetics experiment. Now, as we learned about rate laws, to figure out how concentration affects the speed, we need to change the concentrations. So in mixture two, what you'll do is instead of using the same amount of persulfate, S2O8, you'll actually use half that amount and you'll add ammonium sulfate, which is, for our purposes, just a filler to keep the volume equal. And you'll run a trial with that. So in the next trial, you'll be cutting the concentration of S2O8 and looking at how that would affect the speed of the reaction. What did it do in response? Did it affect the speed? You'll look for the blue color, and you'll take down the second data point. Now, then the third mixture, the third trial, is going to be you use the same amount of S2O8 as the first trial, right? So don't add the filler of ammonium sulfate. Only this time you'll cut the concentration of iodide. Instead of using the full amount of iodide like you did before, you'll use half as much and fill the remainder with a filler, KCl, potassium chloride. So that way you'll be cutting the concentration of your iodide and looking to see how will that affect your speed of your reactions. Once you do that, you'll generate a table much like we did in lecture 2, rate laws, and you'll do the same kind of analysis that we did. What did we do to the concentration of persulfate between trial 1 and trial 2? How did that affect the reaction rate for those trials? And vice versa, we cut the concentration of iodide. How does that affect the reaction rate? Now, really important is to carefully look at the procedure to figure out what are the concentrations that go into this table. Because when we say the concentration for trial 1, we need the concentration upon mixture. So notice that you poured flask A together with flask B and the contents of the beaker. So these concentrations are not going to be the ones that are on the labels of the containers. You're going to have to do a dilution calculation to figure out when everything has been mixed together, what is the concentration of persulfate and what is the concentration of iodide. For your reaction rate, well, we learned in our first lecture that a reaction rate is equal to -1 over the coefficient of reactant, whichever one we're interested in, say persulfate, times the change in concentration of persulfate divided by the change in time. So we're going to use this formula to calculate those reaction rates. What do we mean by delta T? Delta T is that time interval between the start of the reaction and when it turned blue. So that's going to be your stopwatch measurement. What about the change in concentration? How do we know how much persulfate is being used up? Well, if you remember in the diagram, we can trace how much is being used using stoichiometry. The coefficients are our best friends. What we know is that when our beaker turns blue, all of the thiosulfate has been consumed. So what did my thiosulfate start as my concentration? And what does that mean it ended with? And what is that going to be that delta concentration? If I know how much thiosulfate I've used, then take a look at those coefficients in our reaction. How much iodide had to be used up for that much thiosulfate? What's its change? And then finally, more stoichiometry. If I know how much iodide was made during that reaction, then how much persulfate was being used up? So think about how coefficients can be helpful in answering those questions. So there we have it. So what do we expect when we get into lab? This is our first experiment. So first, I hope that you enter lab understanding the tasks you need to perform. There is a pre-lab assignment, getting your lab notebook ready, and it must be uploaded before lab begins. That's what pre-lab indicates. We're going to set up the experiment together. You'll need burettes to measure out the quantities for the trials. And you'll do a repetition to make sure that your data is consistent. And then for this portion of the experiment, that's it. Then we'll clean up, and whatever time is remaining, you can go ahead and start the analysis for your lab report. Get those orders and the finished rate law. Okay, so if you have any questions, please let me know. All right, have a good one.